Hey everyone, and welcome. Today, we're going to break down one of the coolest and most important ideas in modern AI, long short-term memory networks. You'll usually just hear them called LSTMs. This is the technology that basically gave our machines a real working memory, and it completely changed the game for how they understand things like language and video. So let's dive in.
Just think about how you're listening to me right now. You're not hearing each word in a vacuum. Your brain is automatically connecting it to the last word and the sentence before that, creating this constant flow of thought. It's called persistence, and that ability to hold on to context is just how we understand the world.
And for the longest time, that was the million-dollar question for AI. If you want an AI to understand a story or translate a paragraph, it can't just look at one tiny piece at a time. It needs to remember what came before. So how on earth do you build that?
Well, the first big breakthrough in this area came from something called a recurrent neural network, or an RNN. This was really the first serious attempt at building a neural network that could actually remember things.
You see, a standard neural network has, well, the memory of a goldfish. If you show it a movie one frame at a time, by the time it sees the second frame, it's completely forgotten the first one. It starts over from scratch every single time. And as you can imagine, that's not super useful for understanding anything that happens over time.
So the genius of the RNN was this really elegant trick, a loop. You can see it on the left here. The network does its calculation, and then it feeds its own output right back into itself for the next step. It's like it's leaving a little sticky note for its future self. And when you unroll that loop, like you see on the right, you can see what's really going on. It's like a whole chain of networks, each one passing a little message to the one after it. A simple but really powerful kind of memory.
But, like any first draft, it wasn't perfect. While this loop was great for remembering things that just happened, it had a huge, tragic flaw when it came to remembering things from further back in the past. And this slide just illustrates the problem perfectly. Okay, look at the left. If a machine sees the clouds are in the, it's pretty easy to guess sky, right? The clue, clouds, was just a few words ago. But now look at the right. I grew up in France, I speak fluent. To guess the last word, French, the machine has to remember the word France from way back at the beginning of the sentence. And that is what we call a long-term dependency. And here was the killer problem for those early RNNs. As that gap between the clue and the moment you need it gets bigger, the memory starts to fade. It's like the signal gets weaker and weaker with every step until it's basically gone. The network just forgets. It couldn't connect the dots over long distances.
So we have a problem. Our first attempt at a memory network is just too forgetful. We need a hero, and that hero's name is the long short-term memory network, or as pretty much everyone calls it, the LSTM. Now, LSTMs are technically a type of RNN, but they were built from the ground up with one goal in mind, to completely solve this forgetting problem. For an LSTM, holding on to information for a long time isn't a struggle. It's literally what they were designed to do. It's their default state. And you can just see the difference right here. On the left, that's the simple repeating part of a standard RNN. On the right, whoa, that's the inside of an LSTM. It's still a chain-like structure, but each individual link in the chain has a lot more machinery inside, 4 special layers that are all talking to each other in a very specific, very clever way.
Okay, so let's pop the hood on this thing. Let's take a look at the machinery inside an LSTM cell that gives it this incredible memory.
All right, the single most important concept to get about LSTMs is this horizontal line that runs across the top of the diagram. It's called the cell state, and the best analogy for it is a conveyor belt. It runs straight through the entire chain from beginning to end, and information can just cruise along it without getting messed with too much. This is the memory superhighway.
So if the cell state is our conveyor belt, how does the LSTM control what gets put on or taken off? Well, it uses these amazing little structures called gates. You can think of them as little checkpoints with tiny neural networks inside that act as regulators. They can open and close to carefully add new information to the belt or remove old information that's no longer relevant.
The whole process inside an LSTM cell, at every single step in time, can be broken down into 3 main jobs. First, it decides what it needs to forget from its memory. Second, it figures out what new, important information it wants to store. And third, it determines what part of its memory it should output right now. Forget, store, output. Let's look at each one.
Okay, step 1 is the forget gate. Its job is to look at the new information coming in and decide if anything on our memory conveyor belt is now out of date. So, for example, if our model was remembering the subject of a sentence was a man, and then a new sentence starts talking about a woman, this gate would say, okay, that old information about gender, we don't need it anymore. Let's forget it. Next, the LSTM has to figure out what new information to save. This is actually a 2-part process. First, a part called the input gate decides which values it's going to update. Then, another layer creates a list of all the possible new information we could add. It's kind of like one part deciding, okay, I'm going to update the gender, and the other part preparing the new value, female.
And now it's time to actually update the memory conveyor belt. We take the old cell state, use the information from the forget gate to erase the now irrelevant info, and then we simply add the brand new candidate information we just created. So out with the old, in with the new. The memory has officially been updated. And finally, step 3, the output. The network has to decide what it's actually going to do with this memory right now. The output gate looks at our newly updated conveyor belt and decides which parts of that memory are actually relevant for the immediate task. It then outputs a carefully filtered version of the cell state. That's what gets passed on as the final answer for this moment in time.
And that's it. That's the amazing mechanism inside an LSTM. This ability to selectively forget, store, and output information wasn't just a small improvement, it was a total game changer for the entire field of AI. And the impact was absolutely massive. I mean, LSTMs were the engine behind so many technologies we take for granted now. Breakthroughs in speech recognition, machine translation like the early Google Translate, systems that can look at a photo and write a caption, LSTMs were behind all of it. For years, if you had a problem with data in a sequence, LSTMs were your answer.
LSTMs were this incredible leap forward in getting machines to understand context. But you know how it is with AI. The field moves at lightning speed. So the question is always, what's next? What's the next big thing? And the answer to that question, the idea that has really shaped the last few years of AI, is a concept called attention. The core idea is to give the network an even more powerful skill. Instead of just carrying a memory forward on a conveyor belt, what if, at every single step, it could look back over a huge pool of information and decide for itself what to pay attention to?
And this is the thought I really want to leave you with. LSTMs taught machines how to remember. The next frontier, the one we're in now, is teaching them how to focus. So what happens when an AI can not only remember its past, but can intelligently and dynamically pinpoint the single most important piece of its memory at any given moment? It's an incredibly powerful idea, and it's shaping the future of AI as we speak. Thanks for watching.